Hello everyone, in this video I will talk about A4 implementing operations on 360 FS file system image. So this is our 360 file system. So as you can see that in this file system we have several blocks. The first is called super block, and the second is called file allocation table. And followed by that, we have root directory entries. And then we have data blocks. Here, a block is a logical concept. So let's introduce them one by one. For superblock, the superblock is the first area and is reserved for critical file system metadata. And this is the layout. So the first entry is file system identifier, and it has 8 bytes. And for example, in the image disk02x, and the value is 360 fs. And the second field is block size. It has 2 bytes, and you can find the value here. And this is the file system size, block where FAT starts, and the number of blocks in FAT, and the block where root directory starts, and the number of blocks in root directory. So when you read from superblock, you can determine the position where FAT and root directory locate. Before introducing FAT, let's first look at root directory entry. So the root directory entry will record the directory files in this image. So each entry has those following fields, and each directory entry is 64 bytes in size, and the maximum number of these entries within the root directory is fixed. So let's first look at this first field, status. Status has 1 byte, but only 3 bits are useful. So bit 0 is false if the entry is available, true otherwise. And bit 1 is set to true if the entry is for a normal file. And bit 2 is set to true if the entry is for a directory. So we can see that the bit 1 and bit 2 cannot be set to true simultaneously. And the next field is starting block. The starting block is the first block of the file corresponding to the directory entry. And this is the number of blocks in file. Then we have the file size, create time, modify time, and file name. Okay, and for the data, for the date and time stored in a directory entry, assume something like this. This is the first 4 bits are for year, and the next 2 bits are for the month, and then followed by date, hours, minutes, and seconds. So 2 bytes are used to store the year, and 1 byte each is used to store other values. And this results in 7 bytes for each date and time. Then let's take a look at the file allocation table. So file allocation table can be treated as an array of 4-byte integers. And when the file system block size is 256 bytes, each block in the FAT will contain 64 FAT entries. If the block size is 512 bytes, then each block will contain 128 FAT entries. And FAT entries may contain the following values indicating the status of its corresponding file system block. So if the value is 0, which means this file system block is available. and which means it is a free block list and FAT are combined together. And if the value is equal to 1, which means this file system block is reserved, which means it is part of the super block or the FAT. And from the value 2 to this value, this file system block is allocated to some file, and this value is also the address of this block. This figure shows how to locate corresponding blocks for a file. So let's, for example, here we have a file name test, and the start block is 217. Then we want to check whether this is the last block or there is a next block. So we go to FAT to check the entry 217, and we can see that the value in this entry is 618, and this is actually the number of the next data block. And we do the same thing again to check whether there is any following blocks, and we can see that in this 1718 entries in the FAT, the value is 339. So which means the data block 339 is the follow-up block of 1618. Then we go to 339, and we find that the value here is a end of file. So we have, by far, we have found all the data blocks for this file. So there are 3 data blocks, and then we can go to the data blocks to get the content one by one. So in this assignment, we have 3 tasks. So for the first task, we need to write a program that displays information about a 360 file system image. So your code must read in the super block of the disk image and use that information to read entries in the FAT. And here is an example output. So we can see that you need to print out those kind of informations. Then in task 2, you need to write a program that displays the root directory listing for a 360 file system image. And this is an output. You need to print the size of the file and the date, the create time, and the name of the file. In task 3, you need to write a program that copies a file from this image to the standard output of the host console. Okay, so just like this. So in this task, you need to first locate the data block, the first data block for this file, which you need to find this file in the root directory entry, and then you need to go to the FAT to find the following data blocks, and then go to the data block to read them one by one, and copy the content into the standard output. Next, I'll give some implementation details for this assignment. And first, I want to talk about the byte order. So some content of the superblock and directory entries are integers, and these integers are to be written to disk images along with other file system metadata. However, the order in which an integer's bytes are written to a file depends upon the Indianness of the host computer. Let's consider this short program, and which is compiled and executed on the JHub with the contents of some file.bin displayed on the console. So we just open the file with a write mode and write two integers. The first is a short integer and which has 2 bytes, and the integer I which has 4 bytes. So let's compile it and execute it. So we can see that when we write 2 integers into this file and then we display the content by using the xxd command, we can see that the byte order is reversed. So it should be 007F, but what we have seen is 7F00. So the bytes are flipped. Okay. But we are used to reading bytes from left to right, not right to left. Therefore, all the integers in file system metadata must be stored big endian order, as this will greatly help during debugging. In order to ensure this, we can use code in the network library. Okay, let's give an example here. If we add the network library and use the function h2ns and h2nl, and we can see that after using this function and after compiling and rerunning, now the bytes are in the correct order. We also provide 2 structures for you, so which can be helpful when you read super blocks and directory entries. And you will make heavy use of the library functions like fopen, fseek, fread, and fwrite. So here I give a introduction here. So for the first function, file fopen, which will open a file and return a pointer to this file. So we need to give 2 arguments. The first is the file name and the mode. The second is fseek. Fseek function can set the file position of the stream to the given offset. So there are 3 arguments. The first is the pointer to the file and offset, and this is the number of bytes to offset from whence, and whence has 3 constant. The first is seek set, which is the beginning of the file, and seek current, and which is the current position, and seek end, which is the end file. And this function returns 0 if successful, or else it returns a non-zero value. And this is fread. We can read data from the given stream into the array pointed to. So we have 4 arguments. The first is the pointer to a block of memory with a minimum size, and this is the size of bytes of each element to be read, and this is the number of elements, each one with a size of bytes, and this is a pointer to the file. So you can use this function and our provided data structure to read the super block and root directory entry. The next function is fwrite. It is similar to fread, which has 4 arguments. The first is the pointer to the array of elements to be written, and the size of each element to be written, and the number of elements, and the pointer to the file. Okay, that's all for this video.